For centuries, matter was treated as the most reliable element of reality. Cultures changed, governments collapsed, technologies evolved, but the behavior of physical materials remained constant. Light refracted according to known laws. Heat dispersed predictably. Objects stayed inert until acted upon. These expectations were not merely academic. They formed the psychological bedrock of how humans understood cause and effect. The physical world was something you could trust, even if you could not fully understand it. That sense of trust began to erode not with a dramatic discovery, but with quiet inconsistencies. In controlled environments, researchers noticed measurements that did not align with long-established equations. Light beams emerged at angles that calculations said were impossible. Thermal energy accumulated where it should have dissipated. Waves acoustic, electromagnetic, mechanical behaved as though the medium guiding them had rewritten the rules mid-flight. At first, these results were treated as errors, not revelations. Instrumentation was blamed. Calibration procedures were repeated. Environmental interference was suspected. Entire experimental setups were rebuilt from scratch. Yet the anomalies persisted, not sporadically, not randomly, but consistently. When variables were controlled, the outcomes repeated with unsettling precision. Matter was not failing to obey physics. It was obeying physics in a way no one had prepared for. What made this moment distinct from past scientific surprises was its emotional texture. There was no immediate triumph, no rush to publish or celebrate. Instead, there was hesitation. Conversation slowed. Papers were delayed. Scientists hesitated to name what they were seeing, because naming it implied accepting that something foundational had shifted. The discomfort came not from danger, but from implication. In physics, violations of expectation are not unusual, but they are usually temporary, resolved by deeper understanding or corrected assumptions. This felt different. The behavior was not at the edges of measurement, but embedded within the material itself. The same substances, metals, polymers, composites were producing effects that contradicted how matter had been categorized for generations. Density, conductivity, transparency, rigidity, properties once considered intrinsic suddenly appeared negotiable. The deeper researchers looked, the stranger it became. These materials were not exotic in composition. They were not made from unknown elements or cosmic substances. In many cases, they were constructed from ordinary matter arranged in unfamiliar ways. Yet their behavior suggested an internal logic that operated independently of intuition. Matter was no longer just passive substance, it was expressing structure-driven behavior that felt almost intentional. This is where unease entered the room, not fear but disorientation. If matter could be engineered to behave in ways that contradicted expectation, then the distinction between natural law and human design began to blur. The rules had not vanished, but they no longer belonged exclusively to nature. Humans were no longer just discovering physical laws. They were beginning to negotiate with them. Outside scientific circles, the world continued as normal. There were no public alerts, no visible disruptions. Buildings still stood, devices still functioned, but beneath the surface, the assumptions that governed engineering, energy, communication, and defense were quietly being rewritten. The shift was invisible because it did not announce itself. It integrated seamlessly into existing systems, changing behavior without changing appearance. The most unsettling realization arrived slowly. This was not a future problem. It was not theoretical. These materials were already being tested, refined, deployed. The world had not changed suddenly, it had changed subtly. And subtle changes are the hardest to notice until they become impossible to reverse. Matter was not waiting for permission. It was already behaving differently. This was the moment when science paused, not out of uncertainty, but out of recognition. Recognition that the relationship between humans and the physical world had crossed a threshold, that matter was no longer just something to be observed, measured, and used. It was something that could be instructed, shaped, and under the right conditions made to act in ways that challenged the very idea of what was allowed. And so the story does not begin with an invention, or a breakthrough, or a name. It begins with silence, with confusion, with the uncomfortable awareness that the most stable element of reality, the matter beneath our feet and around our bodies, had quietly stopped behaving the way we thought it always would. For as long as humans have studied nature, there has been an unspoken assumption that some boundaries simply exist, not fences you can see, but lines felt instinctively, limits beyond which matter, energy, and life itself were not meant to go. These lines were never written into law, yet they shaped every discipline. They were the reason certain questions were avoided, certain experiments delayed, certain ideas dismissed before they could fully form. In early science, these boundaries provided comfort. Nature appeared ordered, layered, and finite. Matter could be classified. Forces could be separated. Causes led cleanly to effects. Even when mysteries remained, they existed within a framework that felt fundamentally stable. The universe might be complex, but it was not arbitrary. There were rules, and beyond those rules, silence. Philosophers once argued that some properties belonged exclusively to nature. Life could be observed, but not constructed. Reality could be measured, but not redesigned. Matter could be shaped, but not persuaded to behave against its essence. These beliefs were not naive, they were protective. They created a psychological perimeter around human ambition, a sense that some doors were not meant to open. As science advanced, those boundaries were challenged but never erased. Each generation believed it had reached the edge, only to realize there was more beyond it. Yet even then, the idea of a final line persisted, a point where capability would slow, where complexity would resist control. The belief was not that humans would stop progressing, but that nature itself would eventually say no. This belief shaped scientific ethics long before formal codes existed. It influenced which experiments felt acceptable, which questions felt dangerous, which paths were considered unrealistic. The assumption of a natural limit acted as a silent regulator. If something felt too powerful, too invasive, too transformative, it was often dismissed as impossible rather than interrogated as imminent. But these lines were never tested all at once. They were approached incrementally. Each advance crossed a small distance, so small it barely felt like movement. A new material here, a new technique there. No alarms sounded because no single step appeared to cross the boundary. Progress did not leap forward, it drifted. What makes this moment different is not that a line was crossed, but that it became difficult to locate. The boundary that once felt solid began to blur, not because it shattered, but because it was revealed to be conceptual rather than physical. The limits were not imposed by nature. They were inferred by humans, based on incomplete understanding. In retrospect, the belief in a fixed boundary says more about human psychology than about reality itself. Humans need edges to orient themselves. They need stopping points to define responsibility. But nature does not recognize ethical comfort zones. It responds only to structure, interaction, and scale. When those parameters change, behavior changes regardless of expectation. This realization unsettled more than scientific models. It challenged the idea that restraint was built into the universe itself. If matter does not resist transformation, then restraint must come from elsewhere, from culture, from intention, from awareness. And those are far less predictable forces than physical law. Standing at this invisible horizon, humanity did not encounter a wall. It encountered mist, a gradual fading of certainty. The line that once felt definitive did not vanish, it dissolved. And in its absence, the question was no longer whether science could cross it, but whether that line had ever truly existed at all. This is the quiet truth beneath the unease. The boundary humanity trusted was never enforced by reality. It was enforced by belief. And once belief begins to fade, progress no longer feels like movement toward a frontier. It feels like drifting into open space, with no clear signal telling us when to stop. For most of scientific history, matter was understood through its ingredients. Change the atoms, and you change the outcome. Gold behaved like gold because it was gold. Silicon behaved like silicon because of its electrons. This logic shaped chemistry, physics, engineering, entire civilizations of knowledge built on the assumption that behavior was inseparable from substance. If you wanted something new, you had to discover or invent a new material. That assumption began to fracture when scientists noticed that materials with identical chemical composition could behave radically differently. Two samples, made of the same elements, under the same conditions, yet one bent light normally while the other bent it backward. One transmitted energy cleanly while the other trapped it. The difference was not in what they were made of, but in how their internal structures were arranged. At first, this seemed like a niche effect, relevant only at microscopic scales. But as experiments became more precise, a pattern emerged. When structures were engineered at dimensions smaller than the wavelength of light, sound, or heat, the waves interacting with them stopped responding to individual atoms. Instead, they responded to the architecture of the material as a whole. Reality, at that scale, did not care about chemistry, it cared about geometry. This was a profound shift. Waves do not experience matter the way humans do. They do not perceive solidity or color or texture. They respond to boundaries, periodicity, and resonance. By carefully shaping these boundaries, creating repeating patterns of gaps, rings, layers, and channels, scientists realized they could create materials that acted as landscapes rather than objects. The material itself became a kind of terrain that waves had to navigate. What made this discovery unsettling was how unintuitive it felt. A material made of ordinary copper and plastic could guide electromagnetic waves more precisely than rare crystals. A structure thinner than a human hair could control light more effectively than bulky lenses. The behavior did not emerge from strength or density, but from repetition and scale. Small patterns, repeated with precision, began to overpower natural expectations. This is where the language of effective properties entered the conversation. Instead of asking what a material is, scientists began asking what it acts like to a wave. A material could possess an effective refractive index that does not exist in nature. It could exhibit effective permeability or permittivity values that no natural substance has ever shown. These were not approximations. They were measurable, reproducible realities. The deeper implication was difficult to ignore. The laws of physics were not being broken, they were being navigated. The equations still held. Maxwell's equations still governed electromagnetism. Thermodynamic principles still applied. But by designing structure at the right scale, humans had learned how to move through the solution space of those equations in ways nature rarely explores on its own. This realization quietly inverted the hierarchy of material science. Substance became secondary, structure became primary, design replaced discovery as the dominant creative force. Instead of searching the earth for materials with desired properties, scientists began building those properties directly into matter through pattern and form. The material itself became a platform for behavior. At this point, the term metamaterial began to circulate not as a marketing label, but as a necessity. There needed to be a word for materials whose defining characteristics were not intrinsic, but emergent. Materials that derived their behavior not from chemistry, but from design. Not from nature alone, but from intentional arrangement. These were materials that existed beyond traditional categories. What made this transition particularly powerful was its scalability. Once the principle was understood, it could be applied across domains. Light, sound, heat, mechanical stress, all waves, all governed by similar mathematical frameworks. The same structural logic could be translated from optics to acoustics, from electromagnetism to elasticity. A single idea began to ripple outward, touching multiple branches of physics at once. Looking back, it becomes clear that this was not just a technical advance, it was a conceptual one. Scientists did not merely learn how to make new materials, they learned that matter itself is more flexible than previously imagined, that behavior is not locked into substance, that the physical world is, in a very real sense, programmable if you are willing to work at the scales where intuition fades and structure becomes destiny. This was the moment when matter stopped being defined solely by what it is, and began to be defined by what it is arranged to do. And once that realization took hold, there was no returning to the old way of thinking, because the question was no longer what materials exist, but what behaviors are possible. Once structure overtook substance, scientists began to notice something unsettling. Matter was no longer just interacting with reality, it was shaping it. Not metaphorically, not hypothetically, but measurably. Waves that once traveled freely through space were now being guided, redirected, compressed, or expanded by materials that appeared completely ordinary from the outside. Reality itself, how light, sound, and energy moved, was becoming malleable. The first unmistakable sign came from light. In every classroom, students learn a simple rule: when light enters a material, it bends in a predictable direction. This principle underpins lenses, cameras, microscopes, entire optical systems. But metamaterials broke this rule quietly and decisively. Light entering these structures bent the wrong way. Not randomly, not weakly, but consistently. This phenomenon, known as negative refraction, was not an illusion. It was verified across experiments, across frequencies, across laboratories. Negative refraction did more than confuse physicists, it rewrote assumptions. Instead of light spreading outward as it passed through a lens, it could be forced inward. Instead of diverging, it could converge unnaturally. This allowed scientists to design superlenses, optical systems capable of resolving details smaller than the wavelength of light itself. For the first time, the so-called diffraction limit, long believed to be a fundamental barrier, was no longer absolute, not violated but bypassed through design. At the same time, researchers realized that the same structural principles applied beyond optics. Sound waves, governed by similar equations, could be manipulated in parallel ways. Acoustic metamaterials emerged that could block specific frequencies, bend sound around objects, or trap vibrations entirely. In controlled demonstrations, objects placed inside these structures became acoustically invisible, not silent, but effectively removed from the sound field around them. This idea of invisibility demanded careful framing. There was no vanishing, no disappearance. Instead, waves were guided around an object so smoothly that they recombined on the other side as if nothing had been there at all. The object still existed. The wave simply never encountered it. What made this profound was not the visual effect, but the principle. Space itself was being engineered through matter. The same logic extended into thermal behavior. Heat, like light and sound, propagates as energy flow. Traditionally, heat diffusion follows simple gradients, hot to cold, spreading outward until equilibrium is reached. Metamaterials disrupted this expectation. By engineering internal pathways, scientists could redirect heat along predetermined routes, shielding some regions while concentrating energy in others. Thermal cloaks emerged not to hide objects, but to control temperature flow with unprecedented precision. Perhaps the most striking demonstrations occurred at scales far larger than the laboratory. Seismic metamaterial structures embedded into the ground were shown to redirect mechanical waves generated by vibrations or simulated earthquakes. Instead of absorbing energy, these systems guided it around protected zones. Buildings inside remained relatively undisturbed while waves flowed around them, not unlike water splitting around a rock. Earth itself became a medium that could be shaped. What unites these examples is not spectacle, but consistency. The same principles applied across vastly different scales and energies. Light waves measured in nanometers, sound waves spanning meters, seismic waves stretching across landscapes. The behavior changed, but the logic remained intact. Geometry, repetition, and scale were doing the work, not exotic physics, not speculative theories. Crucially, none of this required new laws of nature. Every effect could be traced back to equations physicists already trusted. Maxwell's equations still governed electromagnetism. Wave equations still described propagation. What changed was how humans navigated those equations. Metamaterials did not cheat physics. They exploited its full solution space regions nature rarely occupies on its own. This is why these developments matter far more than their visual demonstrations suggest. These materials are not confined to laboratories or prototypes. Variants are already embedded in antennas, sensors, imaging systems, medical devices, and communication infrastructure. They are quietly deployed, often unnoticed, because their power lies not in visibility but in integration. The unsettling realization is this: when matter can bend waves at will, it controls perception itself. What can be seen, heard, measured, or detected becomes a design choice rather than a limitation. Boundaries once imposed by nature become parameters chosen by engineers. The world does not look different, but it behaves differently underneath. At this point in the story, metamaterials stop being a curiosity and become a turning point. Matter is no longer a passive participant in reality. It is an active mediator reshaping how forces move, how information travels, and how environments respond. And once matter gains the ability to manipulate reality at this level, the question is no longer what these materials can do, but where this logic inevitably leads next. 5. When matter started following instructions, programmable matter. For most of human history, matter was finished the moment it was made. Once forged, cast, or assembled, its role was fixed. A bridge could bear weight, but it could not adapt. A tool could be shaped, but it could not change itself. Even the most advanced materials were passive, capable only of reacting in ways determined at the moment of creation. That assumption held firm until scientists began asking a quiet but radical question: what if matter did not have to remain static after it was built? The first clues emerged from materials that responded to their environment in ways that felt almost biological. Polymers that changed shape when heated, alloys that remembered their original form after deformation, gels that expanded or contracted depending on chemical conditions. At first, these were treated as clever tricks, novel properties with niche applications, but beneath them was a deeper pattern, matter responding not just to force but to information. The shift became undeniable when responsiveness turned into reconfigurability. Instead of merely reacting, materials began to change state deliberately. Structures were designed so that small inputs, heat, light, magnetic fields, electrical signals, could trigger large, predictable transformations. A flat surface folded itself into a three-dimensional form. A rigid structure softened, then hardened again. Matter was no longer locked into a single behavior. It was following instructions embedded within its design. This was the birth of programmable matter, not as a single invention, but as a category. The idea was not that matter had intelligence, but that it could encode rules. Just as software responds to input according to logic written in code, these materials responded according to physical logic written into their structure. Geometry, composition, and internal constraints acted like a silent program, waiting to be executed by the right conditions. What made this revolutionary was that the instructions were not external. There was no computer issuing commands, no centralized controller dictating behavior. The rules were local, distributed throughout the material itself. Each component responded only to its immediate environment, yet the collective behavior appeared coordinated. This is how complexity emerges in nature and now, increasingly, in engineered matter. As research advanced, the boundary between material and machine began to blur. Traditional machines rely on separate parts, sensors to detect, processors to decide, actuators to move. Programmable materials collapse these roles into a single system. The same structure sensed change, processed response, and executed transformation. Functionality was no longer layered on top of matter, it was embedded within it. This had profound implications for sale. Machines become more complex as they shrink, but programmable matter becomes more powerful. At small scales, responsiveness increases, precision improves, energy requirements drop. This inversion made it possible to imagine materials that could assemble themselves, repair damage, or reconfigure on demand without external oversight. Scientists began experimenting with modular systems, tiny units designed to attach, detach, and rearrange themselves. Individually, each unit followed simple rules. Collectively, they formed structures that could change shape, density, and function. The material no longer needed to be assembled step by step. It could become what it needed to be when required. Crucially, this was not framed as autonomy, but adaptability. The materials were not choosing goals, they were responding to constraints. But even this distinction began to feel thin. When matter can change itself to meet conditions, the difference between response and decision becomes difficult to define. The system may not think, but it behaves as though it understands context. Outside the lab, early versions of programmable matter quietly entered real-world use. Adaptive surfaces, soft robotics, medical implants that adjust to the body, aerospace components that alter shape mid-flight. These applications did not announce a revolution. They blended in because adaptability feels natural once it works. The deeper significance of programmable matter lies not in what it does today, but in what it represents. Matter is no longer a final product. It is a process, a platform, something that exists not as a static object, but as a set of potential states waiting to be activated. Once this idea takes hold, manufacturing becomes less about building and more about encoding behavior. And this is the moment when the narrative shifts again. Because once matter can follow instructions, the next step is inevitable. The question is no longer whether materials can change, but whether they can anticipate, whether they can adjust before being told, whether responsiveness itself can evolve into something closer to agency. 6. The threshold where matter began to anticipate. Up to this point, matter had learned how to respond. It could bend waves, redirect energy, and reconfigure itself when conditions changed. But response still implies reaction. Something happens first, and matter follows. The next shift was quieter and far more unsettling. Scientists began to notice systems that adjusted before the environment fully changed, as if the material itself had learned how to expect what was coming. This anticipation did not emerge from consciousness or intention. It emerged from feedback. Materials were designed with internal loops, mechanical, thermal, electrical, that continuously adjusted their own state. Instead of waiting for a threshold to be crossed, they optimized themselves in real time. The result was behavior that looked predictive, even though it was purely physical. Matter was not thinking, it was minimizing instability. In adaptive materials, this meant stiffness that changed in advance of stress, conductivity that shifted before overheating, and structures that redistributed load as soon as imbalance began to form. These systems did not need instructions issued from outside. The rules were embedded. The response was automatic. The effect was resilience that felt almost intentional. This principle mirrored something deeply familiar in biology. Muscles stiffen before impact. Skin thickens under repeated stress. Neural systems anticipate sensory input based on past patterns. Engineers did not copy biology directly, but they arrived at similar solutions through physics. When feedback becomes fast enough, reaction becomes indistinguishable from anticipation. What made this transition significant was its impact on control. In traditional engineering, predictability comes from oversight. Humans monitor systems and intervene when something goes wrong. In anticipatory materials, oversight becomes secondary. the system stabilizes itself faster than human response time. Control shifts from external supervision to internal regulation. At this point, matter begins to feel less like an object and more like a process unfolding continuously. Properties are no longer fixed even moment to moment. They evolve, adjust, compensate. The material is never finished being itself. It exists in a state of constant negotiation with its environment. This change has deep consequences for safety and trust. Systems that anticipate can prevent failure, but they can also behave in ways no one explicitly designed. When rules interact, new behavior emerges. Engineers may understand each component, yet struggle to predict the collective outcome. The system remains lawful, but its behavior becomes opaque. Scientists responded not with fear, but with caution. The more capable these materials became, the more difficult it was to draw clean boundaries around responsibility. If a material adapts incorrectly, where does the fault lie? In the design? In the conditions? In the interaction itself? Anticipation complicates accountability. Yet the pressure to continue was immense. Anticipatory materials offered unprecedented performance. Lighter structures that were stronger, systems that healed damage before it spread, components that adapted to uncertainty instead of resisting it. In a world increasingly defined by complexity, adaptability was not optional, it was necessary. As these materials moved from research to infrastructure, their presence became invisible. They did not announce themselves. They simply worked quietly, stabilizing systems that would otherwise fail. This invisibility made them feel natural, even though they represented a fundamental shift in how matter relates to change. The deeper realization came slowly. Anticipation is a form of power. To anticipate is to shape outcomes before they fully materialize. When matter gains this capability, even in limited physical ways, it begins to influence the flow of events rather than merely endure them. This is the threshold, the moment when matter crosses from passive to adaptive, from responsive to anticipatory. Not alive, not conscious, but no longer inert. And once matter begins to behave this way, the next step becomes unavoidable because anticipation does not remain static. It seeks optimization, and optimization, given time and scale, begins to look like learning. 7. Power without visibility. When material science reshaped the world quietly, by the time these materials reached maturity, they no longer felt experimental. They were no longer confined to research papers or controlled demonstrations. They had moved outward into infrastructure, industry, defense, medicine, and energy systems without a clear moment of arrival. There were no announcements declaring that matter itself had changed. The transition happened the way most structural shifts do, quietly, incrementally, and beneath public awareness. What makes material-based power different from traditional power is its invisibility. Weapons are seen, governments are named, technologies like software announce themselves through interfaces, but advanced materials integrate silently. They alter performance without changing appearance. A structure becomes lighter, stronger, more adaptive yet looks the same. A system becomes harder to detect, more efficient, more resilient yet nothing signals the transformation from the outside. This quiet integration produced a subtle redistribution of influence. Nations and institutions with advanced material capabilities gained advantages not through overt force, but through infrastructure itself. Communication systems became more precise. Energy losses decreased. Detection limits shifted. Entire domains of sensing and control moved just beyond the reach of those without access to the same material logic. Power did not concentrate visibly, it embedded. In defense and aerospace, the implications were immediate. Metamaterials reshaped radar interaction. Programmable structures altered aerodynamics in real time. Adaptive materials reduced signatures across multiple sensing modalities. These were not science fiction cloaks or invincible systems. They were marginal improvements, but marginal improvements at scale redefine balance. When detection becomes unreliable, strategy changes. When resilience increases quietly, deterrence becomes ambiguous. In civil infrastructure, the same principles worked in reverse. Buildings absorbed vibrations before they became damage. Bridges redistributed stress dynamically. Transportation systems adapted to load and weather without manual intervention. These changes did not feel revolutionary because they prevented catastrophe rather than creating spectacle. Success in this domain looked like nothing happening at all. Energy systems followed a similar path. Materials that guided heat more efficiently improved power generation and storage. Adaptive surfaces optimized solar absorption without mechanical tracking. Losses that once seemed inevitable were slowly engineered away. Each improvement was small. Together, they shifted what was economically and physically viable. Energy did not become free, but it became quieter, more stable, more embedded. Perhaps the most profound impact occurred in sensing and measurement. When materials can shape how waves move, they control what can be observed. Detection thresholds changed. Noise floors dropped. Some signals became clearer, others became harder to find. This altered not just engineering, but epistemology, how knowledge itself is gathered. Seeing became conditional. Absence of evidence no longer meant evidence of absence. What made this transformation particularly difficult to grasp was the absence of a single authority guiding it. No global agreement authorized matter to become adaptive. No vote approved the embedding of anticipation into infrastructure. Each step was reasonable, each application justified, each decision local. Yet collectively, they produced a world where physical systems no longer behaved passively. Scientists were aware of this aggregation effect long before the public sensed it. They understood that once materials become platforms for behavior, scale amplifies consequences. A single adaptive structure is a tool. Millions of them become an environment. The world itself begins to respond differently, not because it is intelligent, but because its components are no longer inert. And still, nothing felt disrupted. Daily life continued uninterrupted. This is the paradox of material power. It reshapes conditions without altering experience directly. People do not notice when systems fail less often. They notice only when they fail more. Success disappears into normalcy. This is why the shift carried no clear moment of accountability. There was no single decision to question, no turning point to debate. Power moved from visible action to invisible capability, from ownership of tools to control of environments, from who commands to what is embedded. By this stage, the story is no longer about materials alone. It is about a change in how influence operates in the modern world. When matter itself becomes adaptive, anticipatory, and quietly optimized, power no longer needs to announce itself. It simply shapes outcomes in advance. And this realization sets the stage for the next transition, because once power is embedded into material systems, the final boundary begins to dissolve, the boundary between matter and intelligence itself. 8. Scientists as humans, not architects of destiny. At this stage of the story, it becomes tempting to imagine an invisible force driving progress forward, an abstract momentum beyond human control. But that framing hides a quieter truth. Behind every adaptive material, every engineered structure, every anticipatory system, there were people, scientists, engineers, researchers, not visionaries chasing power, but professionals solving specific problems, one constraint at a time. Most did not set out to reshape reality. They were trained to optimize, to reduce loss, increase efficiency, stabilize systems, improve performance. In laboratories, the questions were narrow and practical. How can this material respond faster? How can we prevent failure under uncertainty? How can structure absorb stress without adding weight? Each answer made sense in isolation. None felt like a turning point. The culture of science rewards progress that works. If a system adapts better, it is adopted. If it performs more reliably, it spreads. There is little space in the lab for existential pause. Research timelines are short. Funding cycles are finite. Problems are framed locally. The broader implications often feel abstract compared to immediate constraints. Responsibility is distributed, diluted across teams, institutions, and years. Many scientists sensed the shift before they could articulate it. They noticed when materials began behaving in ways that felt less like tools and more like systems. When experiments produced outcomes that were correct but unexpected. When design choices created interactions no single person had fully predicted. These moments did not trigger panic, they triggered careful silence. Ethical reflection did occur, but it lagged behind capability. Not out of neglect, but because ethics requires clarity, and these systems resisted clear categorization. Were adaptive materials machines, environments, infrastructure, organisms? Traditional frameworks struggled to keep up. Responsibility became harder to assign when behavior emerged from interaction rather than instruction. What complicates the narrative further is that restraint often came from within the scientific community itself. Researchers debated limits quietly. They delayed publications. They chose not to pursue certain directions aggressively. But restraint is fragile when progress is incremental. Declining to take one step does not stop others from taking adjacent ones. Momentum does not require coordination. This is where the emotional tension deepens. Scientists were not villains crossing forbidden lines. They were humans navigating uncertainty with incomplete maps. They operated within systems that reward solutions, not hesitation. And once a capability exists, the pressure to refine it rarely comes from malice, it comes from utility. The deeper discomfort emerged when scientists realized that control was becoming abstract. They could design rules, but not outcomes. They could predict components, but not always interactions. The materials behaved lawfully, yet their collective behavior felt beyond intuition. This is the hallmark of complex systems. No one is fully in charge, yet everything moves forward. Some researchers began asking questions that had no experimental answer. Not can we build this, but what does it mean if we do? These questions did not fit neatly into grant proposals or performance metrics. They lingered at the edges of conferences, in private conversations, in pauses between results. The science continued, but the certainty did not. This is the moment when the story resists simple judgment. Progress was not reckless, but it was not fully deliberate either. It unfolded through countless reasonable decisions made under limited perspective. Each choice felt justified. The accumulation did not. By recognizing scientists as humans, not architects of destiny, not agents of inevitability, the documentary reaches a deeper honesty. The transformation of matter was not driven by hubris alone, nor by blind force. It was driven by curiosity, pressure, optimization, and the quiet assumption that someone else would draw the line if it mattered. And this realization prepares us for the most destabilizing idea yet, because if no single person crossed the line, and no single moment defined it, then the final question is unavoidable. What happens when the line itself can no longer be clearly identified? 9. Living inside a world that responds to you. At some point, the transformation stops being theoretical. It stops living in laboratories, simulations, and conference papers. It becomes ambient, invisible, ordinary. The most profound technological shifts do not announce themselves, they dissolve into the background of daily life. And by the time people notice, the world is already responding to them in ways they never consciously agreed to. Cities begin to feel different before they look different. Buildings subtly adjust how they distribute heat, stress, and vibration. Infrastructure absorbs shock rather than resisting it. Materials dampen noise, redirect energy, and smooth fluctuations without switches, sensors, or commands. The environment no longer waits for instructions, it reacts. This responsiveness alters human behavior long before it alters human beliefs. People walk differently in spaces that absorb sound. They feel safer in structures that flex instead of fracture. They trust environments that adapt to stress, even if they do not understand how. The material world begins to feel less rigid, less hostile, less fixed. But there is a psychological cost to living inside systems that anticipate you. When walls redirect forces, when surfaces manage energy flows, when structures correct disturbances automatically, human intuition starts to erode. Cause and effect become less visible. Actions no longer produce outcomes in familiar ways. The world still obeys laws, but not the ones people grew up internalizing. This is not fear. It is disorientation, a subtle sense that the environment is no longer passive, that it is participating, not watching, not deciding, but responding in ways that feel intentional even when they are not. The human brain is exquisitely tuned to agency. When systems behave adaptively, people instinctively assign meaning to that behavior. The line between tool and environment blurs. A hammer is clearly an object. A thermostat is clearly a device. But what do you call a building that redistributes stress during an earthquake? Or a material that channels heat away from crowded areas automatically? Or a structure that dampens sound where tension rises? These are not machines in the traditional sense. They are conditions. Living inside adaptive matter changes how responsibility is perceived. When failure occurs, it is harder to point to a cause. When success occurs, it feels natural, expected. The system did what it was designed to do. But who, exactly, designed this outcome? No single decision. No single moment, just layers of optimization interacting over time. The deeper shift happens quietly. People begin to expect responsiveness. Static environments feel outdated. Non-adaptive systems feel inefficient, even negligent. A road that cracks instead of flexing seems poorly designed. A building that collapses rather than redistributes force feels obsolete. Expectations rise not consciously, but culturally. This creates a feedback loop. As environments become more adaptive, humans become less tolerant of rigidity. As tolerance decreases, pressure increases to make systems even more responsive. The world is no longer something to endure, it is something to be tuned. And tuning implies control, even when control is distributed and indirect. Yet adaptability is not the same as understanding. Many of these systems function through emergent behavior responses arising from structure, not commands. They are predictable statistically, but not intuitively. This gap matters. When people cannot intuit how the world works, trust becomes abstract. Faith replaces comprehension. This is where philosophical tension intensifies. Humanity has always shaped its environment, but it has rarely lived inside materials that reshape themselves in real time. The environment becomes less like a stage and more like a collaborator, not conscious, not moral, but active. And in such a world, a new question emerges, not about danger, but about identity. If the world adapts to us faster than we adapt to it, who is shaping whom? Are humans still the primary agents, or have they become variables inside systems optimized beyond individual awareness? This section does not answer that question. It sharpens it, because once people live inside responsive matter, the final transformation is no longer about technology at all. It is about what happens when humanity realizes that the ground beneath its assumptions is no longer fixed and never was. And that realization leads directly to the final confrontation, not with machines, not with scientists, but with the limits of human certainty itself. 10. The question that has no ending. There is a misconception about scientific revolutions that they announce themselves, that they arrive with headlines, debates, declarations, or moments of public recognition. In reality, the most consequential transformations rarely feel dramatic at all. They feel reasonable, incremental, sensible. By the time they are understood, they are already irreversible. This is not the moment humanity crossed a line. This is the moment humanity realized the line was never where it thought it was. For most of history, humans understood the world as something external, an environment governed by rules that could be discovered, predicted, and occasionally exploited. Nature acted. Humans responded. Even the most advanced technologies preserved this relationship. Tools amplified effort, but they waited. Machines executed commands, but they did not anticipate them. Matter obeyed, but it did not participate. That assumption is gone. The systems now shaping human experience do not merely react. They preempt, they stabilize, they optimize. They absorb variation before it becomes disruption. From adaptive materials that redirect energy to algorithmically designed structures that respond to stress before failure occurs, the physical world itself has begun behaving like a buffer between human intention and consequence. This changes more than engineering. It changes causality as it is felt. In classical physics, cause precedes effect. In lived experience, action precedes outcome. But when systems predict disturbances and neutralize them in advance, effect collapses backward toward cause. The world feels smoother not because humans are wiser, but because friction has been engineered out of perception. And friction is how awareness forms. Human cognition evolved in environments where resistance mattered, delay mattered, failure mattered, feedback shaped learning. But when environments compensate instantly, when matter itself corrects, adapts, and shields, the feedback loop weakens. Actions no longer feel consequential in the same way. Responsibility becomes abstract. Agency becomes diffuse. Nothing is taken away. It simply becomes harder to locate. From a scientific standpoint, this is not philosophical speculation. It is measurable. Studies in human-machine interaction already show that when systems automate correction, users disengage from monitoring. When outcomes stabilize, vigilance drops. When environments adapt continuously, humans stop adapting consciously. Adaptation still happens, but below awareness. This is the quietest transformation of all. Language begins to shift. Expectations change. What once felt impressive now feels standard. What once felt impossible now feels overdue. The baseline recalibrates, not through persuasion, but through exposure, not through agreement, but through normalization. And normalization is the most powerful force in human history. No one votes on normalization. No one debates it. It simply spreads through design choices, defaults, infrastructures, and standards. When matter becomes programmable, when environments become responsive, when systems anticipate human presence as a parameter, the world begins to feel less like something humans navigate and more like something that is supposed to work around them. This is not entitlement, it is conditioning. And conditioning raises a question science avoids because it cannot instrument it. If agency depends on the ability to notice consequence, what happens when consequence dissolves into seamless correction? If choice depends on resistance, what happens when resistance is engineered away? If awareness depends on interruption, what happens when interruption is treated as a flaw? The danger, if it can be called that, is not control, it is comfort. A world that responds perfectly does not feel oppressive. It feels supportive, and support rarely triggers scrutiny. This is why no alarm sounds. The systems now embedded in matter do not need persuasion. They do not require compliance. They shape experience directly through physics, not policy, through structure, not instruction, through response, not command. And because they operate beneath interpretation, they bypass skepticism entirely. At this stage, even the concept of a boundary becomes unstable, not an ethical boundary, a perceptual one. Where does the human end and the system begin when environments anticipate needs? When matter behaves as if it understands context? When adaptation is mutual but asymmetrical? Humans adapt psychologically. Systems adapt physically. One is slow and unconscious. The other is fast and exact. That imbalance is new, and it leads to the final realization, the one that cannot be comfortably resolved. The future did not arrive as an event. It arrived as an atmosphere. It blended into daily life so completely that questioning it now feels strange, even unnecessary. The world works. Problems are mitigated. Systems respond. Reality behaves. And yet, something fundamental has shifted in how humans relate to consequence, effort, and meaning. Not because science failed, but because it succeeded too quietly. So the documentary does not ask whether this is good or bad. That framing is too small. It asks something far more unsettling. If the world now adapts to humans faster than humans can reflect on their actions, who is actually learning? And if humans no longer feel the weight of consequence directly, what, exactly, will guide their choices? Because once matter itself participates in shaping outcomes, the question is no longer about technology. It is about awareness. And awareness, once lost, does not announce its absence. It simply stops being noticed. So the final question is not about the future. It is about now. Are humans still acting within the world? Or are they slowly becoming guests inside systems that already decided how things should behave? And if the world keeps responding perfectly, will anyone remember what it felt like when it didn't?